So is this means or proportions?
Proportion.
Proportions, good. So since we agree it's proportions, I can get the P here. Oops, the equals 2 for sure goes up null. And what are they trying to test here? What do they know? What's sort of the
23%.
status quo? What they know from the NSC is that it's 0.23. And of course, they have a strong belief or a hunch of some sort that it's what? Higher than the a hunch is a hunch, but data will speak louder than just their sort of intuition that it might be higher. So they went and did the data collection. So one of the things about hypothesis testing is this. It's very similar to our trial by jury we have here in the U.S., where you would assume, we try to assume unless the media gets a hold of you, you are blank until innocent until proven guilty, right? So our hypothesis, our null hypothesis, is considered true until we can prove it, until proven false. Is that a word, proven? Yes.
Yes.
It doesn't come out of my mouth, it doesn't sound like a word. So innocent until proven guilty. So it has this assumption of innocence until we can find evidence to say otherwise. So you can see how it's starting to get similar, right? What did they do? They collected evidence. So, you know, we're not going to have a prosecution and a defense and all that, but if you think about it, you know, we're going to be able to look at the evidence, and unlike 12 people that go into a room and deliberate over what they think the innocence or the guilty, you know, the not guilty or guilty verdict is. I mean, in statistics, we have a way to quantify our doubt. You know, when you put 12 people in the room, they're doing the best they can with how well the case was presented. But with us, we can say, hey, we can put some numbers behind this and say, is this an unusual finding? Is this typical? What's the probability of this occurring? And then we can start to hash out our decision from there, which is one of the unique things of hypothesis testing. Remember on your second or your third test, you just took one of the 3 things I asked you to do for either means or proportions was to compute a probability. That skill you're going to use on this. So the math you already know. The techniques is just the process that we're learning today. So this is our first step. You're done. Look at that. Step 1 done. Write the hypothesis statements. Step 2, this is the boring step. I'm going to walk you through it. I know it's in your notes, but we're still going to talk through it. Are the assumptions and conditions. I mean, we really want to test this, but we want to make sure that we use the right methods to test it. So we have some assumptions and conditions when we're working with proportions. One is it a random sample? As we read through the problem, is it a random sample?
Yes.
So the people in this consumer group were new to collect the data. It's a random sample. Independent?
Yes.
So what are the assumptions we're making here?
One crash doesn't cause another crash.
Exactly. That the crashes themselves are independent of one another. And I think that's a natural enough assumption. See, these are assumptions or checks we do. The success failure condition. Now this is actually one we can put some numbers to. So we need to multiply n times p and n times q. So what is n? In the end, how many did they use in their sample? 120. If you want to know what p is, just look above your hypothesis statement. You just told me what it was.
0.23.
P is considered equal to 0.23 for the time being. What would that make q? 23% of cars or accidents have the complement of 77. Now, I can look at these right now and know that 23% of 120 is well above 10. But just to have a complete set of notes, what is this product?
27.6.
27.6. So clearly 10 or bigger. 90.
2.4.
And my last one is the 10% condition. So I guess these can have bullets here or 4 checks. So 120 times 10 gives us what?
1,200.
1,200 crashes. So if we're comfortable, yes, Robert?
So why do we use P and Q, not P hat and Q hat, if we're testing this situation? Should we use the probability for the situation?
Well, right now we're assuming P is that the population proportion is at 0.23, and that's sort of what we've been told nationally. So we're going to test that out, and what we're going to want to see is if this testing will yield that our community is higher, or maybe our community is just similar enough to 23%. That kind of makes sense? So we use P and Q here for testing these. So this assumption of innocence here for this null hypothesis gets to carry a lot of weight throughout the problem. So the 1,200 crashes, as long as we think that our region that we're talking about has 1,200 crashes or more in the population, then 120 hasn't overpowered the population. And I think that's easy enough to consider. Doesn't mean it has to happen, but in a year or in several years worth of data, they randomly sampled from several years, then if they've had 1,200 crashes over that period of time, then they're okay. So Baltimore City, they do plenty of crashes, right? So basically what this tells us in the end is that we can use the Z distribution, or the normal distribution. Use the normal model, as we've been so used to using with proportions thus far. That just double checks that everything's in order so that we can use a normal model to approximate some probabilities for what's essentially a binomial. All right, so the first 2 steps finished. The third step is where the math happens. So it said we can use the normal model, so I'm going to use it. So there it is. And every time I draw one of these curves, I'm sort of over-obsessed with where is the middle, what is the middle of this distribution, and how do I quantify how far apart my tick marks are, my 1 standard deviation, 2, and thus 3 standard deviations. So this is a sampling distribution for proportions. So what tends to go underneath here?
P.
P. And if you forget what P is, that's the first thing you wrote down. 0.23. Again, that's part of the null hypothesis being considered true. It gets to be the middle of the distribution. Everything should center around it. We also found the standard deviation of a sampling distribution by multiplying P and Q together and dividing by the sample size. Sample size being 120, and P is 0.23. Its complement Q is 0.77. So this will give me an indication of what
0.0384.
0.038. Excellent. That should go in your calculator pretty easily at this point. Y'all can double check. Now notice here. And if we write down p hat, which we've kind of not talked about p hat much, right? We talked a lot about p, the population proportion, and the sample size. But what is p hat here? It's 120, 38 over 120, as they tell us from their research. What is that? Right.
71.7%.
0.317. So my evidence is 0.317. I'm only going to bother labeling my tick marks to the right, since it seems like that's where my evidence is going to fall. So, goodness, I got to add this.
0.268.
Excellent.
0.346.
All right.
0.344.
So that's 0.268, 0.306, 0.344. So again, right now, the null hypothesis is about shown us as much as it can. It says, hey, we're centered around 23% or 0.23. Our standard deviation should be of the size of about 0.038. And this is, again, the big assumption in hypothesis testing is that the null is true. So all I'm going to do now is just place my evidence into the scene. This is not how they do it, but that's how what LA cops do it. No, I'm kidding. You don't usually place evidence. I'm just going to see where my evidence falls into the scene. Where does it go? Somewhere here. It doesn't really matter. I mean, as long as it's in the right place in the number line. So that's p hat equal to 0.317. And I'm going to shade to the right. I have to have a probability. Probability means I need area under the curve. And I want to know what's the probability that I would observe 38 out of 120 or 0.317 as a proportion. That a value or even something more extreme than that. What would that probability be? Yeah, it's pretty small, right? I mean, it's itty bitty as far as I'm drawing. If you don't mind, let's go through the z-score and all that. I'll show you StatCrunch later, and let's see if we can determine that. So our z, as you see it in your notes, I wrote put a big subtraction on top. I might have put a parenthesis on bottom to remind you something goes down there. No. So, where did we stop along this curve?
317.
That's our evidence. We're going to subtract off the mean. And we're going to divide by. So this is going to tell, I know my answer is going to be 2 point something. I can at least put that up there. 2.29, excellent. So you can see it's 1, 2, and a little bit. So I know about what that size should be. And then I'm going to look it up in z-table.
0.9890.
Excellent, thank you. And it returns this. And you know why I wrote it on the left. That's how the table works. But I'm interested in the red. So to finish this off, what do we get?
1 minus 0.9890 equals 0.02.
1 minus 0.9890 equals 0.011. So something that's more than 2 standard deviations away, you can already start to feel that that seems unusually high, right? With that sort of threshold we talked about, unusual. But then it couples up, as it should, with an extremely low probability, which also we know below 5% tends to be something unusual. So I could say, this is not my formal statement in the end, but this is just sort of wrapping it up.
Did you say like the community groups data is in the 1%?
Yes, we could. There is a 1.1% chance we would observe 31.7, sorry. or more of accidents involving cell phones So there's a 1.1%, we would see this sort of percentage or proportion of 31.7% or higher of accidents involving cell phones. And that's assuming that P is equal to 0.3. A better word than assuming, now that I think about it, would be given. There's a conditional probability here, right? P is equal to 0.23. So all of this has been built under the assumption that the population proportion is 0.23. Yes?
Can we just answer the question, is the evidence strong enough to support the group's claim by saying it's over 2 standard deviations?
Ultimately, yeah, that's what it comes down to. Is it's gone beyond some sort of value we feel comfortable with, and in this class so far it's been 2.
Yeah.
We're going to call that a critical value. Yes, you can do that. I'm bringing it to the probability level because a lot of software packages you get will give you a probability to use to answer your question. Plus, when it's written in sort of research out there in the field, they use probabilities to talk about this rather than that sort of Z-score that we feel comfortable or uncomfortable with. So they take it one more level and they go dig in the table and quantify it with a probability. So remember what we've been trying to groom all semester is that when we see something unusual, right, we start to doubt the assumptions upon which the problem was built. So one of the big assumptions that was in this problem was this first one, the innocence or truth in the null hypothesis. So once I see this kind of evidence that's more than 2 standard deviations away, as Nick mentioned, which corresponds to only a 1.1% chance that would happen in a sampling distribution where this is the center, I start to doubt the assumptions. I start to doubt the truth of the population proportion. So in the end, I'm going to have to double back here to stay within the board. In our 4th step, we're either going to retain the null hypothesis or reject the null hypothesis. What do you think? And again, on Monday, we'll get to some hard, fast decision-making criteria, but right now we're just using our gut instinct. What do you think?
I would say reject.
I agree. You're rejecting because this seems really peculiar in this environment. So what I'm doing is saying, okay, null hypothesis, bye-bye. You're guilty. What does that leave us with? An alternative. We only have one other hypothesis, and that says that the proportion of accidents that involve cell phones in this community is bigger than that national rate of 23%.
Because the sample they took showed.
Mm-hmm. Now, I know some of you in the back are like, this is the most lame thing I've ever seen in my life. Of course it's bigger. It's 31%, right? But think about it. How big is big enough? That's the question. So had we come in and they did the 120 crashes, I don't know how many this would be, but let's say 26% of them had cell phone use. Right there. Would that seem unusual? No, it's less than 1 standard deviation. That could just be sampling variability, right? We know samples vary. From sample to sample, the results are going to vary a little bit. So that would be within what we consider just reasonable sampling variability. So if we saw it here, here, somewhere, but once it gets out here, we're like, that's not sampling variability. That's an unusual occurrence. It's going to force me to doubt the assumption that this is true. So let's write a sentence real quick. The sentence says, it summarizes what we discovered. The sample evidence supports the claim that, and this is where I can go back and go, what did they claim again? You can go back and reread. The percent of accidents involving cell phones is higher than 23%. Since I said percent here, I'll repeat it with a percent. And let's just say the percent of accidents in this community. So I don't have any room to put a caret in there. So percent of accidents in this particular community is higher than 23%. So it's higher than that national rate.